Hi, I'm Andy Mitchell from Photonic Research Systems. In this video I'm going to talk about time-gated imaging, discussing what it is, how you can do it, and what you might find it useful for. In time-gated imaging, we can simply think of the gate as something that controls the detection of photons with time. For gated imaging, the gate can be said to be open when the photons reaching your detector are recorded and end up contributing to your final image. When the gate is closed, the photons are blocked or otherwise not recorded. The shutter on a standard SLR camera is an example of an imaging gate. Usually, it tends to just fire just once to collect an image. Shutters and other forms of imaging gate can be mechanical or electronic. If we think of the sensitivity of the camera being 1 when the gate is open and 0 when the gate is closed, then we get a simple sensitivity versus time graph like this. The imaging technique I'll be talking about today takes this process a step further, using a gate that repetitively opens and closes whilst collecting the image. In this case, the camera records photons from several gates before reading out. The gate width, or time that the gate is open, is 5 microseconds, and the number of gates during the exposure is 10. Therefore, the total time during which photons are recorded is 50 microseconds, even though the apparent data collection time is 200 microseconds. This is quite normal for time-gated imaging. The actual time when the photons are recorded may be much less than the framing time of the camera. So, what is the point of this repetitive gating process? Well, time-gated imaging really becomes useful when the gates are synchronized with another external event, such as a light pulse. The light pulses might be completely synchronous with the image gates, or there might be a user-controlled delay between the two processes. As you might expect, that delay between the light pulse and the gate makes a big difference to the data that's collected. I'm going to demonstrate that with an ImageX time-gated imaging system and a blue LED pulsed light source. This is our setup to demonstrate gated imaging with a pulsed light source. Briefly, we have an ImageX time-gated camera, a pulsed blue LED light source, and a target to give us something to look at. On the right we have a laptop PC running the ImageX control application under Windows 10. To set up our demonstration, first we need to select a trigger frequency. This frequency needs to be compatible with the combination of lamp pulse, delay and gate width that we're going to use. Here I've selected 50 kHz to give a cycle time of 20 microseconds. We're going to set up two independent imaging banks to do our demonstration. First, we select bank 1 and set the lamp pulse to be 5 microseconds. We also set the gate width to be 5 microseconds. Finally, we set the delay to be minus 5 microseconds so that the gate is synchronous with the light pulse. We now select bank 2. All we need to do now is change the delay from minus 5 microseconds to plus 5 microseconds, so that the gate is delayed relative to the lamp pulse. Let's see what happens when we record these two banks. First, we record bank 1, where the light pulse is synchronous with the imaging gate. We see an image of the target reflecting the pulsed light into the camera. Now we record bank 2, where the gate is delayed relative to the light pulse. All we see is darkness, which is what we would expect, as in this case the light is off when the image gate is on. One important application of time-gated imaging is to study fluorescent and phosphorescent materials that exhibit long lifetime emission. There is no strict definition of long lifetime, but for this video it will mean anything from hundreds of nanoseconds to hundreds of milliseconds. Many fluorescence measurements are limited by the amount of so-called background fluorescence. This can be particularly problematic if you are exciting your fluorescence with ultraviolet light. Apart from the fluorescence that you're interested in, you could be getting lots of other emission from dust, glass substrates, and proteins and chromophores in solution. Fortunately, most of these sources of background fluorescence have lifetimes on the nanosecond timescale. So if we choose a fluorescent marker with a lifetime in the microsecond or millisecond range, we can use time gating to effectively suppress that background and allow you to detect your chosen marker with better selectivity. For this demonstration we have a small sample of photocopier paper. It's been dyed with an optical brightener by the manufacturers to make it look nice and white under normal lighting. Because of this, it glows with broad spectrum fluorescence under ultraviolet light. This also happens to be short lifetime, of the order of a few nanoseconds, which makes it quite useful for this type of demonstration. You may notice some dark spots on the paper. This is where I've placed some europium chelate. It's absorbing some of the UV and blocking the light to the paper underneath. The europium chelate itself has a lifetime of just under a millisecond. Let's see what happens as we increase the delay of the gate. So that's all the short lifetime fluorescence rejected. Now let's increase the exposure time to collect more of the long lifetime europium emission. If we go back to the original settings, we can see what a huge difference it's made to the image. As soon as the delay of the image gate becomes positive, the fluorescence from the paper is no longer recorded, and all we see is the long lifetime fluorescence from the europium complex. This process is the basis of a number of important high sensitivity analytical techniques. So that's the end of our video today. I hope you found it interesting. In future videos I'll be telling you more about the ImageX time-gated imaging system, discussing time-gated multiplexing and covering lifetime-based imaging techniques used for remote sensing of oxygen and temperature.